Section 8-5, testing a claim about the standard deviation or variance. The basic idea here is to test a claim about a population standard deviation or variance. In this case, we will use a chi-square distribution. Just to remind us of our notation, we have n as a sample size, s is a sample standard deviation, s squared is a sample variance, corresponding to sigma, the population standard deviation, and sigma squared, the population variance. Now the population standard deviation and variance are the ones that we're looking for, so they're going to have the value of the claim. We're going to make a claim about these parameters. So we got some basic requirements. We want to make sure that the sample is simple and random, and we want to make sure the population has a normal distribution. Now this has a stricter requirement because it uses a lot of other ideas that require it to be a normal distribution. The test statistic is going to be given by a chi-square equals n minus 1 times s squared divided by sigma squared. So in search for the critical values or the p-values, we will be using table A4, or if your calculator has some special program, we can use an inverse chi-square. In any case, the table or the chi-square distribution requires a degrees of freedom, and our degrees of freedom here is going to be n minus 1. Here's one more page on the requirement that it has to be coming from a normal distribution. A reminder of some properties for the chi-square distribution. Chi-square starts from 0, and it's it's skewed to the right, and it starts to look a little bit more normal if your degrees of freedom gets larger and larger. But it's not symmetric, unlike the Z or T distributions. Here's some examples of some graphs of a few different degrees of freedoms of the chi-square distribution. Let's do an example. Listed below are the heights in inches of from a simple random sample of 10 supermodels. We want to consider the claim that the supermodels have heights that have much less variation. So let's use a 0.01 significance level to test the claim that supermodels have a standard deviation that is less than 2.6 inches. So in our sample of 10 supermodels, we have a standard deviation of 0.894 and a variance of 0.7997. The requirement checks, well, the sample is simple and random, and to check for normality, there's this normal quantile plot that we can do, but we'll just assume that it's normally distributed. Alright, the first three steps are as follows. The claim is that the standard deviation is less than 2.6 inches. We write that as sigma less than 2.6. The opposite of the claim is sigma is bigger than or equal to 2.6, and so the second step contains a condition of equality that will replace our null hypothesis with sigma equals 2.6, and then we will keep our alternative hypothesis to be our claim, sigma is less than 2.6. We have a significance level of 0.01 that was given, and we will be using the chi-square distribution because we are testing a standard deviation. We compute the test statistic. Chi-square is going to equal to 0.852. Since we have 10 supermodels, we have a degrees of freedom of 9. And so we will look for our critical value in table A4 with a degrees of freedom of 9. Degrees of freedom of 9, alpha is 0.01, so this is a left tail test because sigma was less than 2.6, and so the area to the right is what we need to put into the table A4, and since the area to the left is 0.01, the area to the right is 0.99. With 9 degrees of freedom, we get our critical value to be 2.088. Our test statistic is quite smaller than that, and closer to 0, so our test statistic is actually in the critical region. So because our test statistic is in the critical region, we will reject our null hypothesis. And because we rejected our null hypothesis, we can then conclude there is sufficient evidence to support the claim that supermodels have a height with a standard deviation that's less than 2.6. So we rejected the null hypothesis that says our standard deviation was equal to 2.6, and so we should be able to support the original claim. Now, some programs, some calculator programs might have a way to compute the p-value, and if you do that, you get a p-value of 2.897 e to the negative 4. That's essentially 0.0002897, and that is clearly less than 0.01. So because our p-value is less than 0.01, we would still reject the null hypothesis and come to the same conclusion. If we were to do the confidence interval method, which is not preferred, we would be careful about switching from a left tail test to a two-tail test, because confidence intervals have two tails. So our left tail test was a 0.01 significance level, and if we change this into a confidence interval, we're going to have two tails, and the two tails are going to be 1% on the left side and 1% on the right. So that's going to lead us to a confidence interval where we have a 98% confidence. Note that it's not 99% confidence. So in any case, if we follow this through, we would get a confidence interval that would be between 0.5 inches to 1.7 inches. And in this case, these values do not contain 2.6. In fact, these values are pretty much on the left side of 2.6, which leads us to the same conclusion that the critical, the standard deviation is less than 2.6. All right, that's the end of Chapter 8.